So hopefully, for those of you who want to get code installed, that worked. What I want to do is start getting into not just reading code, but actually writing some code in a very simple way. To do that, we're going to go back to the same notebook, the Hello World notebook or the credit scoring notebook, and we're going to change something. So let me go back to that tutorial. This here, credit scoring. And if you think about what the notebook has, there's clearly we're not going to change the first part of the import statements. That's stuff that's the plumbing. Data set, we could swap out and do a different data set or change the split range, but that's just general machine learning things. I want to focus on the stuff that's specific to Fairness 360.
So was the condition credit decision example, was it?
Yes.
Okay, thank you.
Yes. So, so step 3 was computing the metric, and that's what I want to focus on changing, because there's many metrics, and you can try to change to different metrics. So let me go down to that step 3. Over here. And you see that we created a binary labeled data set metric. Okay, remember that name, I'll show you that in a second. We passed in some parameters, and then all we basically did is, given that object, which is right over here, metric orange train, we called this method. So this is the key thing. This is what we're going to change. Mean difference. That's one of probably around 70 different metrics that are available in Toolkit. And we want to try something else. Okay. So code works now, and we're going to change it, and you want to know, well, what are the options? What other metrics can I call, and how would I find that out? So before we actually change the code, I want to try to answer that question. By going back to the main page. Okay, so on the main page, there's this right here, get code, which is a link to GitHub, one of the links in the beginning. I'll show you that in a second. And then there's this very valuable link to the API documentation. Okay? So let me go to that one first. And this is a view of the toolkit, how it's broken down. It's essentially a directory structure, sort of hierarchical. And you'll see there are basically 4 pieces to it. There's something called algorithms. Oops. There's algorithms, which are mitigation algorithms, right? This is the code that the now 10 different pieces of code that will mitigate bias in some way. And you can see, I think it was Kush talked about before, there is 3 different flavors of that. There's pre-processing on the data set. Rachel mentioned this as well. There's in-processing when you're training the classifier, and then there's after the fact. So the 10 different mitigation algorithms are grouped in these subdirectories according to what flavor they are. Okay? They're all done, independently by different researchers, but some work on the data set, some work on the algorithm that's training the classifier, and some work after the fact on the predictions that the classifier gives. And that's how it's structured. We're not going to play with those in this part. Then there are data sets, and these are basically the representations of data sets. It's not the actual raw data, it's a representation of that that's consistent in Fairness 360. So the idea here is we want to be able to mix and match. Given a data set, we want to have a standard interface so that we can apply any of these 10 algorithms. We want to get the power of multiplying all different data sets, all different algorithms, and so it's orthogonal. So that's what a data set is. I'm not going to go into much detail there yet. Explainers, I'll come back a little bit later and talk about what they are. That's a pretty simple thing. What I want to focus in this session is on metrics. Right? So these are the places where the actual statistics happens, where you're saying, we said before, given privilege and unprivilege for a particular attribute, what's we said was minus 17% with one metric. And these are grouped in different classes. So I'll show you these in a second. So each class has one or more metrics inside, those are basically metric calls. So I'll get more details in a second, but what I wanted to just give you was, first of all, show you that this API exists, which is a nice way of navigating the code without you having to get down to details. And then you can click on something to get more details. So in fact, it's a good accident on purpose. So this was the one we saw in the code, binary label dataset metric. And it tells you some parameters to the class. And then below here are the various methods you can call. You can call base rate, you can call consistency, disparate impact, and mean difference. Mean difference was the one that we actually had in the notebook. Okay? What's nice about this is you get a textual description, you get a nice equation for those who can understand this and it's more intuitive to them. And then if it's actually something that's being published, you get a reference to the paper. So all this is there. And I just want to contrast that to the actual code. There's another way of looking at this. So this is a nice markup language that's automatically generated from the code. And if we go to the code, okay. So that was the API docs one. Now we can go to the get code link, which goes to GitHub. And I'll show you a mirror image, hopefully, a mirror image of what we just saw in the GitHub one. So all the stuff we talked about lives in a directory called AIF 360. That's where the package comes from, as Karthikeyan mentioned before. The notebooks and other things are in these things, docs, examples, and tests. So if we click there, you'll see a structure that's very similar. There are the algorithms, the mitigation algorithms. There are the data sets, which is that interface to the data sets. There are explainers, which we'll talk about a few sessions later. And then there are the metrics. So if we click on metrics, we now see those same classes we saw on the interface. And here's our friend, the binary label dataset metric. We can click on that and see the actual Python code. And now this is just a question of what do you like to look at, right? Do you like to look at this, or do you like to look at the interface before? They're equivalent. What you see here are stylized comments that automatically generate that interface you saw on the web page, right? So here it's just in text with these stylized comments. There's a tool that creates it. So you can look at it here, and you can see, here's an interface for non-positives, and you can actually see the code. Here's the return statement that actually returns the value, non-negatives, and if I find it, we'll see mean difference. Up here somewhere. There it is, mean difference. Okay. Which is just basically an alias for that. So that's why I want, this is the purpose of this is to let you know how you can kind of learn the system. One way is the API way. Right this way, which is, I think, a way that quite often developers try to learn and program against the system, is they actually navigate it, see what they need, see what the interface is, and just call it. They don't necessarily care about the details of how it's implemented. Or, if you want to know the details, you can go to and actually see the code. If you're interested in doing your own algorithm, doing your own metric, then certainly you want to see the code and understand the what's been done and how you can do it. Any questions on that? Yes, please. What do we use to generate the magic? Sphinx, yeah. Yeah, it's highly recommended. I mean, this has gone around. I first saw this. It certainly happens in Java. There's something called JavaDoc. C++ had it as well. It's very nice. The general idea is in your code you write stylized comments, and then some magic tool generates beautiful. In the old days it was web pages. Now it's notebooks or whatever. So I won't take up too much time. Let's go back to the task at hand. Exploring. So what we want to do, or what I'd like you to do for those who want to get the great rush of changing code and getting it to run, is go right here, and where it says mean difference, change it to something else, which you see in the API. Okay? So you want to look at the API for the same binary label dataset metric. Right? You can do that in the API view, the nice formatted view, or in the actual code, and change it to something else. Like, I want to tell you what to do. This spelling test, Canada. disparate impact. That's how you spell it. And I think everything else should work. And you'll get a number out. So what will happen is we'll load the data set, we'll still okay, we'll still load the data set. The privileged groups, unprivileged groups are the same. The data split will be 70%, and then now we will compute a different metric. And you know, you can leave the comment as it is if you want. It'll say difference in mean outcomes, but that's not what you're actually telling it. You'll be telling it disparate impact. If you want to get extra credit, you can change the text to disparate impact. And then down here, the message will print, and you'll get hopefully a different number. And then if that works, you can keep the mitigation the same. And then you can come down here where you compute the metric on the mitigated data set. And here you would change the mean difference to disparate impact.
So we've done the modifying the first example, and now I'm going to briefly go through some guidance on choosing which of the mitigation algorithms to choose. I touched on this when I did the demo. If you remember, there was pictures of and actually Kush also touched on this early on. So, you know, you've got the pre-processing algorithms, you've got the in-processing, and then you've got the post-processing. So, that's ahead of my slides. First of all, we've got lots and lots of algorithms. So, okay. So here we are, the pre-processing algorithm. So that's an algorithm applied to training data. We've got an in-processing where you're actually training a fair classifier, and then the post-processing where you're applying it after you've got your classifier to the predicted labels. And so one of the partly it's a very pragmatic choice. Can I modify, do I have access to the data? Can I modify the data, in which case you can apply a pre-processing algorithm? Or, can I, am I allowed to change the actual algorithm, the classifier, then you can do an in-processing, or if it's totally black box, then you are only able to do the post-processing. So that's one of the ways that you can think about what you can do. We do recommend that mitigating earlier is better, mitigating your data if you possibly can. This allows you the most flexibility in your pipeline and to correct as much bias as possible. Now you can sort of apply mitigation at all stages, but you probably don't want to, it's overkill. And so just like in machine learning, where basically there's no one best algorithm, that it depends on the data set you've got. Similarly, it's the same thing for when you're choosing your fairness, your fairness algorithm. Your mitigation algorithm. Now, some of the algorithms are matched to specific fairness metrics. So, for example, some of the algorithms actually take the fairness metric and optimize with respect to that. So, if that's optimized, pre-processing, you'll see. But really, you should you can try the different algorithms if you have access to the data and it's a total white box. Try them and see which works best in your circumstances. Somebody said something about hacking bias. So maybe, I don't know what the guidance is on that, but we could have a discussion of that. How about that? Right. So here, basically, even though certain algorithms are designed for certain fairness metrics, it actually may do well on another one that you want to look at. So, there's this interplay between the metrics and the algorithms.
So, actually, because we have
yeah, I'm going to use this 360 CX environment. Yeah, so you can see that we already have the examples folder here. So hopefully I can just create a Jupyter notebook. Yeah, so going to open this. Okay, so this is a live notebook. So the goal of this tutorial is we have this dataset called medical expenditure panel survey dataset. Basically, the idea is that it's a nationally representative dataset that is collected from individuals in the United States. And besides a lot of things, it talks mainly about the health expenditure that is incurred by individuals in the United States. So what we are going to do is, and it's collected pretty much like 2 times a year. So we are going to see, we are going to actually take one of the years, we are going to train a model and observe that there is bias in the model with respect to race, and in terms of predicting the medical utilization. And then we are going to debias it and show that bias has reduced because of the debiasing algorithms we have applied. But then we are also going to demonstrate a couple of more interesting things. One is we are going to try and see if we can explain the reasons behind the prediction. And there is a very popular algorithm called LINE, Local Agnostic Model Explanations. So we are going to use that in order to show feature level importance scores and show that what are the the main factors behind like a few predictions. And the other thing we are going to do is we trained a model in one of the past years. We are going to apply it in one of the recent years, and we will see that even though the model was debiased in the past year, there is a drift because of the changing population and everything, right? So we are going to demonstrate that part. And so it kind of demonstrates the importance of like this continuous learning type of scenario, because data sets can keep changing over time. And once we demonstrate it, we will show that this can be again mitigated using some of the algorithms that we have in the toolbox. So that's the goal. Like we'll basically take like a few years worth of data, train in the past year, and then show that it has debiased debiasing has happened. And then as we go to the future, even though it was debiased in the past, it is no longer bias free, and the bias is actually increasing. So and then we will retrain and debias again. So that's like the overall overview of this tutorial. And this tutorial is nice because it demonstrates lots of things about the toolbox. One thing it demonstrates is it shows like 2 different ways of debiasing. One is by pre-processing, one is by in-processing, right? So it trains also an in-processing algorithm to debias. And it also uses like multiple different base machine learning algorithms like logistic regression, random forest, and so on. So I'm going to pick and choose because of course we cannot run everything in this short time. But if you want to, like have a real experience running this, it's very easy to run. I mean, you can just follow the instructions and it should hopefully work. So yeah, this is the table of contents. I will skip that. So this is what the use case is, right? So a data scientist develops a fair utilization model, and a developer deploys it, and goes into production. The model might start drifting because of temporal shifts in the data set, and then you can go back and debias it again. Right? And the data set we use is called MEPS, Medical Expenditure Panel Survey. It's actually a very, very popular data set among healthcare researchers. So just to show how the data set is collected, so it's collected in multiple panels. So like you can see, these are years and these are panels. So each panel spans like 2 years, right? So panel 18 spans 2013-2014, panel 19 2014-2015, and panel 20 2015 and 2016. Okay. So and the sensitive attribute we are going to use is race. So the privileged group is going to be whites, and the unprivileged group is going to be non-whites, everyone else. And the feature that we are going to use is utilization. Basically, it shows how much healthcare services are utilized. And we define high utilization to be greater than 10 for this variable, and low utilization to be less than 10. Okay, so again, like Mike was mentioning, so this is the standard procedure for bootstrapping. So we have to load the data sets. So we are loading like 3 data sets, 19, 20, and 21, which are the 3 panels. And then we are also loading the fairness metrics, and we are also loading a few other scikit-learn things. And then in terms of bias mitigation, we are going to try out 3 different algorithms. One is reweighing, which is a pre-processing algorithm. The second one is prejudice remover, which is an in-processing algorithm. And the third one is pre-processing disparate impact. We're also going to use line in order to figure out the explanations. Right? So I'm going to execute this cell. Fairness, yeah. These are explanations of individual predictions. Okay, so it executed, so I think we are safe. So and then, like usual, whenever we have a data set, we have to divide it into train, validate, and test. So here, this dataset class itself contains a split method that can divide it into train, validation, and test set. So we are going to take the panel 19 data first, and we will divide it into train, validation, and test set. So and we'll print out some statistics of the dataset. So loading the dataset takes a bit of time. So so this has loaded the data set, and we are printing out some statistics of the data. So it shows the train, validation, and test data set sizes. It shows the protected attribute named as race, and these are the privileged and unprivileged groups, and these are the features of the data set. Right? And then we will compute the metrics for the original data. So we will look at the mean difference. We can see that the odds are stacked up against the unprivileged group because we get a negative mean difference. Right? So now we will train a logistic regression model on the original panel 19 data, right? So we'll train a logistic regression model. This is all like, again, standard scikit-learn model. And then since this is outputting scores, we have to figure out what's the score threshold we have to use. And for that, we will use the validation data set. And we will print out this curve, display this curve. Basically, this curve shows the balanced accuracy and 1 minus disparate impact against the classification thresholds. We know that disparate impact should be really close to 1 in order to declare the model to be fair, which means 1 minus disparate impact should be really close to 0. But then you can see here that 1 minus disparate impact is quite high, 7.6, right? So this is really not a fair model at all. And we'll also show some classification metrics, which is here we are showing like average odds difference, which is basically the average of the difference between false positive and false negative rates of the classifier that we have, the logistic regression classifier. Again, it has to be really close to 0, but you can see that it's negative, which means it's unfavorable to the unprivileged group. Right? So then we'll print the summary metrics. So here it's showing at the best accuracy that we can get is 0.76, 76%, and 1 minus disparate impact is 0.6, which is actually quite high, and the average odds difference is 0.1831. Okay. So what I'm going to do is I'm going to open a text editor so that I can copy paste all these things, and I don't have to go back and forth. Right? So, actually, I have.
Average odds difference?
Yeah.
You said you had the convention that if it's negative, it's how much it's affecting the.
Yeah, and that's the conversion we have.
Yes.
Except for disparate impact, because its fair value is 1. So if it is less than 1, it is unfavorable to the unprivileged.
So any ratio if less than 1 is worse for the privileged group, and greater than 1 is worse for the for difference measures is positive.
Yeah, that's the convention. So now we only tested it on the validation data set. Now we are actually going to test it on unseen novel test data. And you will actually see that the odds are still stacked up against the unprivileged group. So I already pasted this here. So this is the first result that we have, right? So it's the first result we have. Now I'm going to skip the random forest part because it's pretty much the same thing. Just using random forest instead of logistic regression as the base model. Okay. And the results actually look remarkably similar, which kind of shows that the model itself is not inducing the bias or something. So now we are going to mitigate using a pre-processing technique. We are using the of course we can use any other technique that we want. And so that data transformation has happened. And as we saw here, the mean difference has become 0. And this is exactly what we had, what we discussed like a few minutes back. Now, we are going to use this reweight dataset in order to train a new model, which we call as the fair model. Right? And we'll also get the fair thresholds for this. Like here you can, first of all, here you can see that at this point, which is the threshold that we are going to use, the mean difference, the 1 minus disparate impact has actually reduced to like 0.3 from 0.6. Right? So there's actually a bit of fairness already introduced here. Right? And similarly, the average odds difference has come closer to 0. It's about 0.01 now. Now, I'll show it on the test data because that's the baseline that we'll have. So the best balanced accuracy is 0.75. It reduced from 0.77, but it just went down to 0.75. And then 1 minus disparate impact went from 0.57 to 0.24, which is actually quite a bit of improvement. And look at the average odds difference. It went from minus 0.2 to 0.01, which is actually remarkable improvement in terms of fairness. Right? So now we can claim that we have actually debiased the data set, and we have applied it, we have created a model from the debiased data set, which we can call as fairer.
This is the general, this is the average of the metric of the whole data set, not protected.
No, it's the
Right? Do you have anything for calculating these metrics, protected attributes?
Well, I mean, it's basically
Oh, no.
comparing multiple protected attributes.
Yes.
So you have to actually have at least 2 protected groups in order to do this thing. because you're comparing the two groups. I think what you're asking about is more like an individual fairness metric, like a consistency or something. And it's very easy to compute that also, like it's just calling like one more function. So it's easy to compute that also. But there is no guarantee that it will improve or reduce. It really depends, because these algorithms are tuned for making the group bias better. So it really depends on the data set, algorithm, and a lot of other things. Okay, so we also have this, so this is for, okay, yeah. It's going to throw errors on the random forest part, but I'm going to ignore it because we didn't run the random forest part. Okay, so okay, so we are coming to this prejudice remover, which is basically an in-processing technique, so it's a bit different from what we have seen now. So what prejudice remover does is, it attempts to learn a logistic regression classifier while making sure that the mutual information between the protected attribute and the predicted outcome is small, which means that there is going to be really small correlation between the protected and the predicted outcome, which is like one of the definitions of group fairness, right? So that's what prejudice remover is doing. So it's optimizing a mutual information based metric. So now we are going to see how much it improves the bias, how much it improves the fairness. So it's running. I'm going to go to the test part because that's what we use as comparisons. So the test part, so after debiasing, the prejudice remover reduced the accuracy to 0.68 from 0.77, and it also improved the disparate impact more than reweighing plus logistic regression, and it also made the average odds difference really good. The only problem is it reduced the accuracy much more than logistic regression, right? So yeah, so this is one way to like, so doing these sorts of things will actually like, even printing out stuff will let us compare like different things. We can actually make a decision on how we can, which ones to use depending on the constraints that we have. Like if you don't want like a lot of reduction in accuracy, or if we really want to reduce, we really want to make it fair regardless of the accuracy rate. So there are like certain constraints like that that you can, like do using these sorts of simple things. So
in that case, would you make like a hyperparameter search? Like if
there is a hyperparameter, you can search for it, yes. And one hyperparameter we have actually here is the classification threshold. So like if you want to, for example, have like, you can place the threshold here, right? And you can get like a really small average odds, like really close to 0. But then you would have reduced accuracy to like 0.6. So those sorts of things can be done. Okay, so I'm going to skip the disparate impact part because I think we need time for other things. I'm going to go to the like I said, I will skip the errors that I saw with random forest because I didn't run it. Now the question is, I have this model trained on panel 19. I'm going to deploy this on panel 20, right, which is a data set from the next year. So here I'm taking that model and I'm deploying it on panel 20. So I'm going to see how fair it is, right? So it's loading the data set takes a bit of time. So okay, now it's done. Panel 20.
in this case, because building is the data from here, but if you
Yeah. Like with panel 20 deployment data, the disparate impact is 0.11 and the average odds difference is 0.06, which is still within like acceptable limits. So now what we are going to do is we are going to see how we can explain the individual predictions. Like Kush said, we are not explaining the fairness. Actually, during the break, a participant was asking us, like, can you explain the fairness? Like, can you say apportion the fairness to like different features? We don't have anything like that yet, but that's an interesting thing, and we hope he will implement it for us. So this is the line model. And what we have is actually an interface with the line code. It's basically line is basically an explanation package. It can explain like individual predictions. So here we are looking at two different data points, and we are looking at the outcomes, which are the number of visits, and seeing which features explain the number of visits. So for this person, for example, the cognitive limitation and the joint pain, it explains the number of visits. And for this person, like smoking, explains the number of visits, high number of visits. So those sorts of things can be done. So now comes the more important part here. So we want to test this on the later years, which is the panel 21 deployment data. So we are testing that on it, testing the model on it. So again, it's taking a bit of time to do the modeling stuff. We have an interface to Line. Yeah. We have to install Line, but we have an interface from AF360 to Line.
Because I know it's very hard, since you need some statistics, where we have to use Line. H2O AI has managed to productionize with part of some data explanation. Yeah, it's still part of also this version of Line. Okay, so you have a normal.
Yeah. Anyways, so this is the measures from the panel 21 deployment. So I pasted it here. Like if you look at panel 20 and 21 and compare the measures, one thing you can clearly see is that the disparate impact, 1 minus disparate impact, has increased by twice. So I mean, we may like it and we may not like it sometimes, which means we have to retrain. And this is definitely a drift, right? So it was really small before and it has increased now. So this is a drift, and what we want to do is we want to retrain, relearn the fair model, right? So what we will do is we'll take the current data, we'll do reweighing on it, and we will relearn the fair model based on the latest data, because this happened due to drift, right? And one thing we can see is during the redeployment, the fairness has actually improved from 0.22, it went to 0.14. So, and the average odds difference has also improved, like slightly, but still significant. So yeah, I mean this is just a way for us to think about what happens when you have like a real data science pipeline with like. And these are like, this data set, like I said, is a nationally representative data set of healthcare expenditure and so on. So it was a good experience for us to look through it and figure out what are the things that we have to do in order to make it work in the real world.
It went a bit fast with the explanation and follow.
Yeah, we can go back to the explanation part.
Well, it was not, still. What I wanted to ask was like, can you, the bits that calculates the model drifting or the fairness drifting, if we can call it like that, can you isolate it in a way that I could from a networking production that, for example, takes all the data with the prediction from last week and calculate it, and then you can see your fairness deteriorating with time. So you can monitor your model and then just launch it and try it, and you can start a bit. It's interesting, because we don't have, I think, specifically but
Yeah, I know people are a little disappointed that they couldn't install the AI 360, but I can promise that we will definitely help over the Slack channel. Whether we are here or not, just post your questions wherever you are, and we are very active, in responding to anyone. So, and we'll definitely be able to get you up and running sooner or later.
So you might remember before when we looked at two different ways of just understanding the toolkit. This was the API view, using mitigation algorithms. These were the data sets, which are the wrapper around the underlying data. And then we talked a little bit about the metrics. And there was this curious class called explainers, which sounds like a lot of the questions that we were asking before in terms of explaining decisions, but that's not it. These explainers are trying to explain the metrics, right? So there's a whole big field on how do you explain machine learning decisions, interpretability or explainability. This is about, can you explain a metric, okay? And it's not necessarily what I think someone was asking before, right? Someone was asking. What it is, it's more of a software engineering trick, I guess I would say. And so the idea is, we saw in the first tutorial, we called one of the metrics, we got a number back, right? And then we were responsible for writing the text, right? So if you remember that notebook. We were responsible for writing the text. And it was some kind of string, and it said the average difference for blah, blah, blah is blah. And then we went and we changed that metric, and it said, oh, by the way, you might want to change that string, right? So that's an error that's likely to happen unless you're really a diligent software engineer. And the question is there a better way, is there a way that the toolkit can help you on that, right? So that's what the explainers do. And there's two flavors. One is a text explainer. I'll show you that in a second. And the basic idea, let's see. This is just the interface, which could be sufficient. I think I'll go to the code. No, I want to go to the notebook. Let's go with that. Okay. Sorry. Go back there. Yeah, it's a cool thing to do. That one, this one. Okay, so remember I said earlier there are tutorials, and we're going through all three of those. Those are notebooks with a lot of text trying to walk you through things. And then there are other examples, right, that are just notebooks. So if you look at notebooks, you get into the repository, it lives under that examples directory I mentioned earlier. And you see there's a whole bunch of things called demo. Okay? And the one I want, and here's the one that's the Hello World tutorial. It says tutorial. These are 3 tutorials. And the demos are other things. So there's a whole bunch, over 10 different ways of seeing examples of playing with AI 360. What I want to look at is the explainers. So this is a notebook just to illustrate the use of explainers. Okay? Very, very simple. Here we have a data set. We do our usual prep for computing a metric. And then we call an explainer. So we create an explainer for that metric, and then we actually call the num-positives metrics. This is just like what we did before, where we were looking at a particular API, we got a number back, and we had to string ourselves with a string and then a number. And now what we're doing is we're saying, well, let this explainer figure out what the appropriate string is to print. Okay, so here it is. For this metric, it's printing out number of positive outcome instances, and that's the value. So it's printing it out, the string ourselves. We don't have to actually do that. Right? So it's a nice trick of sort of software engineering to say, well, wait a minute, maybe you have a better idea of what the right string is. Of course, you can customize it yourself like we did in the Hello World example, but this is one where it's saying, I don't care, give me what the default string essentially would be. And you can see, the difference here. for different metrics, mean difference, disparate impact, and it gives a little more, a little more richness. Maybe you don't have to be an expert necessarily on what is mean difference, what is disparate impact. It's telling you a little bit. So text is very important, but sometimes we get information and we want to pass it on to another piece of code. Right? And text is great for humans to read, but not necessarily good for another piece of code to read. And that's where a JSON can really help, where you pass the information in some structured way so that a subsequent module can then take it in a structured way and then manipulate it. And here you'll see that there is some, I think it's essentially the same, or is there more? There's a little bit more here. Right? So this is a JSON object. This is a standard way of basically having fields and values. It came from the JavaScript world. And you'll see, what is the name? This is the field. So the object has a field called metric. That's num positive. So it's a way of actually having a string num positive you can actually print out if you need to. What's the message? I think we saw that up above, right here. Positive outcome instances. That's that message. You might want just the number by itself, and then you have that, 700. Then you get some more things. There's a description of what is this thing, and we saw that, this one. And then this is really nice. Ideally, what's an ideal value for this? You may have seen earlier, some metrics 0 is good, and some metrics 1 was good. So it'd be nice to get that, to know what is good and what's not good. And so that's what's going on here with the JSON format. And this was used in the web demo, if you remember, from about 3 hours ago. Rachel was showing the web demo, and the strings being printed out. That's what was used.
There's other things that we could consider adding on, which would be going well beyond the text output or the JSON output. So the action recourse paper that I mentioned that's going to be presented here could be in the explainer class if implemented. There's a lot of recent work on counterfactual fairness or causal sort of notions of fairness. So those sort of methods could also be implemented by the explainers.
Sorry, so you talk on the first day, you present how to make like a recommendation, how one was the slide.
Yeah, this isn't us. This is Burke Oostrom is the first author. He's a postdoc at Harvard, so it's his paper. But yeah, it's a good paper. I would recommend us attend. But yeah, it kind of figures out what is the sufficient change needed to change your outcome prediction. So this is a credit scoring one, and it would say that you need to increase your most recent payment amount from $0 to $700, and then you need to put a one, for example. So it's specific to linear models in Harvard, but I think they're working on this one as well. This counterfactual stuff is, again, it's trying to decompose why certain metrics are appearing as they are. So then the final industry example that we have is on face image classification for attributes such as the gender of the person. So this has been in the news quite a bit. At last year's FatStar conference, there was a paper by Joy Bellamy and Timnit Gebru, which was entitled Gender Shades, and it received a lot of press and so forth. So Joy and another person, Deb Raji, a couple days ago at AIES presented another paper, which is also on face technology, and it was also covered in the New York Times, I think, on the 24th of January. So this is clearly an issue. I mean, people care a lot when face classifiers get attributes wrong. And just as a side comment, IBM Research today released this new really comprehensive face classification data set as well, called diversity in faces, which is the first of its kind, and I encourage you all to look. So going to the actual demo tutorial. Again, so I won't run it. I'll let Karthi did all the running. I'll just walk through the notebook just in the interest of time. So. Okay. Alright, so if I go back to this tutorial that we have, actually reopen it, actually the notebook here, just to look a little better. Alright, so here, this is on the UTK face dataset. So this is a dataset that already has attributes in it. So this includes age, gender, and so forth. Interestingly, it has a really wide range of ages, from 0 to 116. So it's very comprehensive in that regard. So in terms of the import statements here, since it is a computer vision problem, the best sort of models for the machine learning part at least are kind of the neural network sort of approaches. So we'll use Torch, PyTorch here. And there's a little bit of image manipulation done where you just get everything as resized images and so forth. So in step one, again, nothing really different than what we've seen before. We are loading and processing the images into the AI 360 dataset. Format, we are going to consider whites as one of the groups and others as the other group. So others is anyone who's not Black, Asian, or anyone who's not white, Black, Asian, Indian. So this is people with Hispanic, Latino, Middle Eastern, and so forth. We'll consider the task to be gender classification, and the privileged group would be class 0, which is whites, and the unprivileged group is group 4, which is the others. Here, favorable and unfavorable doesn't have so much meaning because in a gender classification task, getting someone male versus female, there's not one that's particularly favorable, but to keep things standard, we do require all the data sets to have a favorable group defined. So now we're just loading the images and so forth. We will, as before in other examples, learn a baseline classifier. This one happens to be a convolutional neural network. Fairly simple and straightforward, just to illustrate the point. So we're not trying to have some benchmark beating based classifier. And similarly, we'll split into train and test, batch sizes and so forth, for the neural network. Here's the creation of the neural network. We train it. We get the training, and now the interesting part of the trainer side is that we will get the following fairness metrics. So these are on the original data itself, no depricing done. So things like equal opportunity difference are in the range of -0.07. And now we will apply one of the pre-processing approaches. And in this case, among pre-processing approaches, the only one that we can do is reweighing, because the others work on the features, and the features themselves, if you manipulate them in images, they don't end up as images very simply. So this is the only pre-processing that can really work. We have some existing work that's not part of the toolkit yet, which we call the fairness scan, which would be a pre-processing approach that would actually require to change the image pixels as well. So we do this. We look at what happens on the classifier using the reweighed versions, and at the end, what we see in the comparison is, so again, just looking at equal opportunity difference, we went from -0.07 to -0.06. So there's not much change. This one actually didn't have too much bias to begin with on this, but it's actually more interesting to then break this down and look at the equal opportunity difference by age group and see what happened before and after. So in particular, there's a couple of age groups where the change was quite a bit. So among 10 to 20-year-olds, we reduced improved the fairness quite a bit, and also for the older individuals. For some of the other age groups, there was not much change. So that was kind of disguising how much improvement we were seeing on the outcomes for this one. So just to kind of show you that there's different types of data that can be looked at in different sort of industry use cases and so forth. So that's kind of all the prepared material that we had. We have, I guess, 9 more minutes, so we can kind of discuss with you guys where to go next on this. So as a user, as a contributor, or anything you might discuss with us. So the floor is yours. Yep. Yeah.
In the last video, the notebook you showed,
Yeah.
well, we used the reviewing algorithm. I have read what it does, but intuitively, does it mean that it can tell you what kind of data you need to collect to make your data set better?
It's not intended to be used that way, but that is a good usage, potentially good usage of it. So, in fact, if you have binary outcomes in 2 protected groups, all you have is actually 4 weights. So for each combination of protected attribute and outcome variables. So those 4 numbers are the ones that you're applying at the end. And so yeah, I mean, the ones that have the smallest weight are the ones that you have the most data for. But it's not a one-to-one mapping of how much data did you have versus what the weight is. It's more of what's the effect of that amount of data to the outcome. So it might, I mean, directionally tell you that these are the groups that you need more data for, but the number itself isn't going to tell you that you need this much more. Other things you guys wanted to talk about? Yeah.
So, I don't know what this always this stuff. There seems to be some kind of accuracy mitigation. And I was wondering, it's not exactly like the result, if more populace drops after mitigation process, I wonder whether researchers also look at the rich data points, the error actually propagates, whether it actually brings a equivalent scores, whether it comes from
Yeah, I think that's a great point. I think, yeah, it's not a question of the tools. I mean, you can use all these tools to do all that analysis. I think, yes, it should be done, and also it's important to note that when we are saying accuracy, it's with respect to the original distribution that we had, which already is in place in it. So it's not necessarily a good thing to even measure accuracy with respect to the validation set that we have. So it's something that I haven't heard talked about too much at this conference, but I think it needs to be talked about more is how do you really measure accuracy when you have a bias problem already. I guess everyone, actually, Karthikeyan might come up and we can just kind of say goodbye to you guys. And we're all, most of us are going to be around the rest of the conference. So, so feel free to find all of us at any point, and we're more than happy to follow up over time or in these next 2 days as well. So, so we're very happy that you stuck around, and we hope that you become active users at minimum and contributors if that's your thing as well. Thanks.
And the Slack channel lives on beyond this tutorial. So you may see the whole workspace. There's a bunch of channels, and you'll see people have been asking questions already before this tutorial. So feel free to ask either in the tutorial or in the general channel.